Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. So today we are going to discuss about the module Structure of Ceramics Part 5, and in this module we will be discussing about structure of Ionic ceramics, and this module is in continuation with the previous module. So this module is from the paper Ceramics. So students, let us see what we are going to learn in this module. So we will be learning about the structure of ionic ceramics with HCP packing of ions, that is hexagonal close packing of anions. Next, we will be learning about the basis of the formation of woodside structures, corundum structures, and the structure like lithium niobium, ilmenite structures, and rutile structures. So similar to FCC, that is face-centered cubic packing of ions, many ceramic structures are also based on another type of closed packing of anions, that is HCP. So here HCP correspond to hexagonal closed packed structures. So in this category, we will look at the following structures, and which are, the first one is the woodside structured compounds. Next, we will be discussing about corundum structured compounds. Next is ilmenite structure compounds. Then we will be discussing about lithium niobium structured compounds, and then lastly we will be discussing about rutile structures. So students, let us discuss the first compound, that is woodside structured compound. It is represented by Mx. So the compounds with M2 plus X2 minus stoichiometry are woodside structured compounds. Some of the examples are the polymorphs of sphalerite structure compounds such as zinc sulfide, zinc oxide, silicon carbide, and so on. Here we are representing zinc sulfide as ZnS, zinc oxide as ZnO, and zinc carbide as SiC. The coordination number of both anions and cations is 4. This means that the coordination number of anions is also 4, and for cations it is also 4. It is similar to that in sphalerite structure compounds. So in this case, the anions form a HCP lattice, that is hexagonal cubic lattice, with 1/2 of the tetrahedral sites with bications. So the only difference to sphalerite structures is that here anions pack in the form of ABC, ABC, and so on, stacking. Now let us learn and analyze how this woodside structure look like. So you can see in this figure, you can notice that all tetrahedrons point in one direction, that is along C-axis of the unit cell, and they share the corners. Here the lattice type is primitive and HCP. The motif, as we have discussed in the previous module how to calculate the motif, so for here M is 0, 0, 0 and half, 2/3 and 1/2. Whereas for X it is 0, 0, 5/8 and 1/2, 2/3, 1/8. So in this structure, you can see that the yellow correspond to M, that is the yellow colored atoms correspond to M, and the black color atoms correspond to X. Now let us discuss the structure formation in woodside. So let us take the example for zinc oxide, that is ZnO. So you can see on the right hand side the structure of zinc oxide, where the blue circles correspond to A-type atoms, that is O2 minus. The blue colored small atoms correspond to zinc Zn2 plus at Z is equal to 1 by 8. Whereas the purple colored circles correspond to B-type atoms corresponding to O2 minus at Z is equal to half. Whereas the green colored small atoms correspond to Zn2 plus atoms at Z is equal to 5 by 8. There is another atom that is green hollow correspond to A type, that is O2 minus, but the position is at Z is equal to 1. So you can see here the layer by layer filling in woodside and a unit cell which is formed, which is similar to woodside structure, which we have discussed in the previous slides. Now the next compound is corundum structured compounds. The formula for it is Al2O3. Such compounds are M2O3 type stoichiometry. The alpha alumina or sapphire. So we are representing alumina or sapphire with Al2O3. So in this case, the parent compound is alpha alumina or sapphire, that is Al2O3. Some of the other examples for the corundum structures are Cr2O3, that is chromium oxide, Fe2O3, that is iron oxide. The anions which are present in the structure form a HCP lattice, where the 2/3 of octahedral voids are occupied by the cations to maintain the stoichiometry of the complete structure. In this case, the coordination number for M atom is 6 and for X atom it is 4. So here M correspond to cation and X correspond to anion. This arrangement preserves the charge neutrality, as you can also verify using bond strength formula. So this can be best viewed when we look in the example which is shown in the next slide. So students, you can see the structure formation for the corundum on the right hand side of the slide. So this can be best viewed when we look at the basal plane of 0001 plane of the unit cell and start filling the interstices. So this plane is represented by the dotted line, and here you can see that the blue colored circle correspond to O2 minus atom of the first layer, whereas the blue colored filled small atoms correspond to Al3 plus present in the first layer. So in the first layer there are blue colored A atoms with small blue colored filled Al3 plus. Now comes the second layer. So the second layer is also consists of O2 minus and Al3 plus, which overlaps and fills the voids over the first layer. So B colored, that is red colored with B written, correspond to O2 minus, and blue filled small atom correspond to Al3 plus, representing the second layer. After the filling of second layer, some voids are still present which are covered by the third layer, represented by A in green circle corresponding to O2 minus and blue color filled small atoms, that is Al3 plus. Whereas there are some vacant positions which you can see in this figure by a cross sign in a circle corresponding to vacant octahedral sites. So in this case, one unit cell consists of 6 layers of the oxygen atom, which we'll see in the next example. So students, you can see a view of 101 bar 0 plane of corundum, where you can see the arrangement of atoms of oxygen as well as aluminium. So in this case, the arrangement of atoms are in AB, AB, AB and so on. So you can see the side view which we have seen in the previous slide, and it shows that the 001 plane is pointing upwards, whereas 1 2 bar 1 bar 0 plane is pointing towards right hand side. So the red colored fill atoms correspond to oxygen and the green atom correspond to Al, whereas the cross sign representing the voids, or we can say the vacant octahedral sites which are present in corundum. So now comes ilmenite structure. So the stoichiometric formula is AbO3, but it is not a perovskite structure. So students, don't confuse with the perovskite structure, because perovskite structure is also AbO3. Here, the parent compound which we will be discussing is iron titanium oxide. So it is FeTiO3. So Fe is for iron, Ti is for titanium, and O is for oxygen. So various other examples of ilmenites are cadmium titanium oxide, that is CdTiO3, COTiO3, that is cobalt titanium oxide. Next is chromium ruthenate, that is CrRHO3. Next is FeRHO3, that is iron ruthenate. FeVO3, iron vanadium oxide. Lithium niobate, that is LiNbO3, magnesium GeO3 and MgTiO3 and so on. So the atomic arrangement is very much similar to Al2O3, except the alternative layers of iron and titanium in place of aluminium. The coordination number for both iron, that is Fe, and titanium, that is Ti, remains octahedrally coordinated. So, O is coordinated by 4 cations, that is 2 iron, 2 Fe and 2 titanium, that is 2 Ti. Now, let us see the structure formation for ilmenite structures. So, as we have discussed in the previous slide, that the stoichiometry of ilmenite compounds are AbO3 types. So, there are 3 types of atoms which are present in a structure, that is A, B and O. So, you can see the example which is shown on the right hand side of the slide. So, in this case, the 3 atoms are iron, oxygen and titanium. In the present case, there are 3 layers which are present, and there is a vacant octahedral site which is similar to that case which we have discussed previously. Now in the present case, the A atom and the blue filled iron 2 plus forms the first layer. Then the second layer is formed over the first layer by filling the voids of A layer. So the second layer is formed by B circle atoms and the violet colored small atoms, that is titanium and O2 minus. Similarly, the third layer is formed over first and second, filling the voids of them. So the third layer consists of Fe2 plus and O2 minus atoms. However, there are still vacant octahedral sites which remains there and are represented by a cross sign. So students, the whole structure consists of 6 layers of oxygen, as you can see in this figure. So the coordination number for both iron and titanium remains octahedrally coordinated, while O remains coordinated by 4 cations, which we have discussed in the previous slide. Now, a side view of the structure of ilmenites on 101 bar 0 plane is shown below in this slide. This shows that the columns of cations along the C-axis with 2/3 filling of octahedral sites whose area or which alternatively filled by iron and titanium ions and then followed by vacant sites. So in the previous slide, we have seen that first layer is there, over that second layer is there over the voids, and then third layer is formed. But still there are some vacant spaces which we are representing by vacant octahedral sites. So this figure also represents the same thing. Here the red color big circle correspond to oxygen, green color small circle correspond to iron, that is Fe, and blue color small circle correspond to titanium, that is Ti. However, the cross correspond to the vacant octahedral sites. So the arrow pointing the columns of face sharing the octahedra. Now let us discuss about lithium niobate structures. Such structures are very much similar to Al2O3 structures, except that aluminium sublattice is substituted in an ordered manner by lithium, that is Li, and niobium, that is Nb ions in the same layer, unlike an alternating layer in iron titanium oxide, that is FeTiO3. The parent compound, that is lithium niobate LiNbO3, is ferroelectric in nature and hence is technologically very much important in wide range of applications. The lithium niobate also has high anisotropic refractive index and it shows birefringence which is changeable by the electric field. So this behavior is due to the ferroelectric nature of lithium niobate. So as we apply the electric field, the properties of a material changes, resulting in birefringence. Such materials are mainly used in electro-optic devices. So electro-optic devices are those where electrical and optical phenomena are involved. Now, let us see the structure of lithium niobate with 0001 plane. So you can see the atomic arrangement of a layer in lithium niobate structure. Here, yellow colored big circles correspond to oxygen, green colored small circle correspond to lithium, red small circles correspond to niobium, and the cross correspond to the empty sites which are present. So you can see that there are various empty sites which are present. You can see the cross-sectional view of the lithium niobate structure which we have seen in the previous slide. So the arrangement of the atoms are in AB, AB, AB sequence and so on. So here red circle correspond to niobium and green circle correspond to lithium. So here the arrangement of lithium and niobium is shown. On the right hand side of the figure, you can see the direction of 0001 plane, whereas the bottom arrows correspond to the columns of octahedral sites. So these columns correspond to the sharing points among themselves. Now comes the rutile structure. The polymorph of titanium dioxide or TiO2 is the rutile structure. So the other forms of the rutile structures are anatase and bruchite. It is formed by quasi-HCP packing of ions. Half of the octahedral sites are filled by cations, whereas other half is filled by anions. This results in the structure formation of the rutile structure, which is tetragonal due to slight distortion. In this case, anisotropic diffusion properties of cations are there in TiO2. A large and anisotropic refractive index is observed in such structures having higher birefringence, and such materials are used as pigments and in non-toxic properties. So students, you can see the unit cell of the rutile where titanium atoms and oxygen atoms are shown. So rutile has a tetragonal unit cell, which we have discussed, with the unit cell parameters of around A is equal to B is equal to 4.5 angstrom and C is equal to 2.9 angstrom. So in the present case, the titanium cations have a coordination number of 6, meaning that they are surrounded by an octahedron of 6 oxygen atoms. The oxygen anions have a coordination number of 3, resulting in a trigonal planar coordination. Rutile also shows a skew axis when its octahedra are viewed sequentially. So you can see on the right hand side where you can see the oxygen octahedras. The rutile structures are most commonly observed to exhibit a circular growth habit with preferential orientations along their C-axis, where the C-axis is 001 direction. This growth habit is favored as the 110 facets of rutile exhibits the lowest surface free energy and are therefore thermodynamically most stable. The C-axis oriented growth of rutile appears clearly in nanorods, nanowires, and abnormal grain growth phenomena of this phase. Now let us see the structure formation for a rutile structure. You can see the titanium and oxygen ions arrangement where a small blue circle corresponds to titanium, yellow correspond to oxygen, and cross correspond to empty octahedral sites. So, as we have discussed earlier, the oxygen and titanium ions are arranged in a rutile structure where the titanium cations have a coordination number of 6, whereas they are surrounded by the octahedras of 6 oxygen atoms, which you can see clearly in this figure. So students, let us summarize what we have learned in this module. So students, we have learned about ionic solids. Let me recall that ionic solids where the anions form the base lattice whilst the interstitials are completely or partially filled with cations or partially filled with cations. Typically, the HCP structures, that is hexagonal close packed structures, are those based on woodsite, corundum, lithium niobate, ilmenite and rutile structures. So these all structures are presented in this module in detail and their phase formation or the structure formation is also cleared. So the top view and the cross-sectional view for each structure has been understood in this module. Thank you.